Let's begin this lesson with a quick review of what we learned from the Boyle's Law lab. We know that pressure is exerted on a container when it is filled with some gas particles. Now, pressure is force over area. So if you take the total number of collisions that the particles exert on the container and you divide that by the total surface area of the container, then you would get the overall pressure that that gas exerts on its container. From our lab, we know that pressure times volume will always give us a constant. Okay, PV is equal to some constant. Okay, we will deal with what that constant is in another lesson. Now, this formula is quite handy because it allows us to examine a system, a container filled with some amount of gas. It allows us to examine that system before and after a change, whether it is in pressure or in volume. So imagine you had a container full of gas and you knew its volume and its pressure. Well, if you were to compress that container down, or if you were to allow the gas to have more space to expand into, you would be able to calculate the new pressure and the new volume of that system. And it's quite simple mathematically. For example, here are two containers. We see that they both contain the same number of gas particles, 5 in each. Let's pretend that this one is sitting at 5 atmospheric ATM. Okay, and let's say that this container right now is at 2 liters. If we compress that container down to 1.8 liters, what then would be its pressure? Okay. So for this kind of question, we can utilize this relationship PV is equal to a constant really simply. If we know that the first container, okay, let's say it's P1 V1 is equal to a constant, and we know that the second container, let's call that P2 and V2 is equal to a constant, and that these two constants are the same because I haven't changed any other condition in the system. Temperature is the same, the number of gas particles is the same. So if the two K's are the same, then we can say that P1 V1 is equal to P2 V2. So all of a sudden, I have a handy dandy little formula to help me calculate the changes of this container before and after the decrease in volume. So then we just go ahead and sub our numbers in. Pressure of the first one is 5 ATMs. The volume of the first one is 2 liters. Okay, and that is going to equal to the pressure of the system afterwards times the final volume of the system afterwards. And then it's just a simple plug and chug, and we should have our new pressure. I will leave that for you to do. The final answer is 2 sig figs. Okay, let's have a look at 2 more examples of how this formula works. A mass of gas occupies 1.25 liters at a pressure of 101.3 kilopascals. The pressure is changed to produce a volume of 0.59 liters. What is the new pressure? As soon as you see a question where there seems to be a system in the beginning with a set amount of conditions, and then there is some change made to that same system, then that should hint to you that the formula in question is some sort of equation where its initial equals to final. And we've seen this before when we did concentrations with dilutions, where C1V1 is C2V2. Okay, so P1 V1 is equal to P2 V2. Okay, the initial pressure is 101.3 kilopascals. The initial volume is 1.25 liters. And that should give us the pressure of the second system, which is actually the same system, but different conditions, times by the second volume, which is 0.59 liters. Okay, we punch that into our calculators. 2 sig figs to finish. Your calculator will give you 214.6 kilopascals, which you can then round up to the correct number of sig figs. This would be 210 kilopascals. Okay. Remember, just a reminder that when you're rounding, we only round up once. So this 4 here is under 5. So we keep the next digit at 1, at 210. We do not use the 6 to bump up the 4 into a 5, which then bumps up with 1 into a 2. That would be a two-step rounding, which is a no-no. On to our last example. A 10-gram sample of gas occupies a volume of 8 liters at STP. What volume does this gas occupy at standard temperature and 300 kilopascals? Okay. So this here again is a before and after situation, because you have some gas at STP, which stands for standard temperature and pressure, and then afterwards it says standard temperature, so the temperature does not change, but the pressure has gone from standard pressure to 300 kilopascals. That 10 gram there doesn't really matter. It's just telling you that there is a 10-gram sample of gas in the container, but nowhere in this question does it say that some of it leaked out or the number of moles has gone up or gone down. So mole stays constant, temperature stays constant. The only thing that changes is pressure, which would then lead to a change in volume. Let's talk about STP. This is a good spot just to review what that stands for. STP stands for standard temperature and pressure. Standard temperature, you guys remember what that is? It is 0 degrees Celsius. Okay. And standard pressure is equal to 1 atmospheric or 101.325 kilopascals. Okay. It's the same pressure, just conveyed in different units. In this question, because the second pressure is given to us in kPAs, we will go ahead and use the kPa version of the standard pressure. So then we set up P1V1 is equal to P2V2. The pressure in the beginning is 101.325 kilopascals. The volume in the beginning is 8 liters. The pressure final is 300, and the volume final is what we are looking for. Punch out in the calculator. Be careful of sig figs. This 300 number right here is actually just 1 sig fig. So we will round off our numbers to represent 1 sig fig. The final volume that you get should be 3 liters. Okay? The unit is liters because the question started off with liters. Okay? Be careful of your units. Do not guess what the units are. Always take a look at your question to see what units went into your formula to get what units should come out. And that's it. That is Boyle's Law. Goo out.